Thanks. So I'm Charlie, this is Chris. We're going to talk to you guys about automotive hacking and CAN buses and stuff like that. So if you saw my keynote, I talked a lot about hacks that are like super awesome and fun, but probably you'll never see in real life, and this is another example of that. That's basically all I do. Okay, so who are we? I don't know. I talked about me earlier. Chris is a guy. You want to say it for yourself?
Usually I'm doing Windows heap stuff, Windows exploit stuff, and decided that it was time for cars.
So we're not actually mechanics, even though we have official mechanics clothes on today. You might not know, but believe it or not, we're not certified mechanics yet. So what are we going to talk about? So first we'll talk a little bit about the cars we used and why we chose them, and then what the computers in the cars are, and sort of how the bus works overall. Talk about all the standards you had to know to understand what the heck was going on. And then we'll talk about how we injected messages and how you do that, and what the effects were. And then if we have time, we'll go into getting firmware off of the devices and how you can reverse that. So the story starts, like we're not the first ones to do this. Back in 2010, 2011, some academics from University of Washington and University of California, San Diego wrote a couple papers about exactly this stuff, like CAN bust and affecting the car. And they wrote the first paper was about how the things worked and how you can inject messages and the effects that would have on the car, which is basically exactly what we did. And then they wrote a second paper about how you could attack remotely. So they showed how through the Bluetooth in your car, they could remotely get code execution and then send CAN messages. And then they also showed you could put MP3 into a car, and there was a bug in the parser for the MP3 in the radio, and they could get code running that way. So anyway, like that's the same thing. We never did the remote part. We only did if you are somehow on the CAN bus already. But they did the same. They did what we did, and then another step. But the one thing that they didn't do was release any information about what they did. So like there's this video, you can see, this is like a screenshot from the video, and there's this huge black box. In the video, this guy walks across the street, and he like remotely attacks the car, gets it to unlock, and he gets the car to start, and he drives off in it. And when I saw the video, I was like, holy shit, he just stole someone's car. And that's why they blacked it out, because they didn't want him to go to jail. But it turned out that they blacked it out because they were scared to release the exact car model that they used. And likewise, in the paper, you can see, instead of showing the actual like messages that they sent, they like dotted out some of the things so that you wouldn't be able to like replicate their work. And so a big thing about what we wanted to do is talk about, we release everything. So we released all our tools, all the messages we used. So if you want to replicate what we did, you can follow exactly along and do that. The other thing that we did that was different than what the academics did was we had cars that had more sort of fancy technology in it than their cars, and so that enabled us to do more kind of attacks. Like for example, their car didn't have any sort of automated steering, while ours did, so that allowed us to do some stuff with steering. I don't know, anything else you want to say?
Yeah, I mean, I think Charlie and I were both very intrigued by what the academics did, but they didn't release any information, so we figured we'd do the opposite and release everything.
Right, so it took us 9 months to do the whole project, and we're still sort of working on related things. If you wanted to repeat what we did, maybe it would only take you 3 months because of all the tools we released. So we're trying to save everyone from having to go through all the pain that we went through. All right.
Yeah, so car hacking is hard. In the regular exploitation world, if you want to attack something, right, you download a piece of software, and you can start reverse engineering it right away. Targeting cars is a bit harder. We had to actually find cars that had the features we wanted to try to attack. And that actually took us like a month just to find the exact cars we wanted to use. So it ended up being difficult just to get the automobiles.
All right, so tell them why we took the cars.
So we took the cars because they were affordable. Originally, I think we wanted some Ferraris and Lamborghinis to work with, but funding didn't permit getting those cars. So we had to find cars that had features such as automated steering. The car will parallel park itself, and assisted braking, or a pre-collision system, as they call it. So we needed specific features to, we realized if a computer was controlling portions of the car, we were hoping that we could do it as well. Working conditions for me on every day is laptop there on the couch. I look pretty relaxed, rocking a pretty wicked suntan, if I do say so. Working conditions in the car, unfortunately, were a bit difficult. The cars usually weren't running. So in the winter, you have Charlie freezing outside with hooded sweatshirt on. And in the summer, it was super hot, but we could only roll down the windows. So the conditions in the car kind of weren't pleasant to be in, especially since it took us so long to do this.
Yeah, we went through lots of seasons, and it was either too hot or too cold. It was almost never.
Yeah, ever. You want to attach to a target with regular software? It's just as easy as sipping drinks in a cabana in Las Vegas. Attaching to a car ends up being a bit harder, and you end up bleeding from your hands a lot, it seems.
Yeah, especially us, because we're used to typing, and it's like we're not used to manual work.
I'm not very good at mechanics work, so I was always busting my knuckles off bolts and bleeding everywhere all the time. Disassembly, right? There's probably a lot of people in this room are familiar with reading disassemblies of computer programs. You're looking at code, you generally have an idea of where an entry point would be. Cars, on the other hand, require a bit more disassembly. We wanted to physically locate computers, so that involved ripping the car up. They would usually give you, we both had accounts on our mechanics website for Ford and Toyota, respectively. And they would say things like, here's 28 steps to remove the dashboard of the car. And I was like, crowbar, and just ripped it right off. Just pried it and ruined it, because I didn't care. We're not going to be using these cars when we're done, so we didn't really care if we damaged them. Debugging, again, is a whole different story when you're dealing with cars as opposed to software. Software, you have a nice debugger. It's pretty easy. You can set breakpoints. If a process crashes, you restart the process and be on your way. Debugging in a car is a bit more difficult, as Charlie shows here. In the Ford, you're basically cutting wires and reading network traffic and trying to relate that to physical attributes of the automobile, such as braking or steering.
Yeah, like here, like the car wasn't working right, and I knew I had obviously cut a bunch of wires, but I thought I had them hooked up right, but I don't know. It's hard to figure out. Like one of them isn't hooked up right, or one of them's touching something.
Yeah, especially I think since we don't have much experience with electronics or automobiles, it was pretty difficult for us at times.
There's so many times that if we would have known a mechanic, it would have saved us like a month.
Yeah,
because
absolutely.
we had no idea what we were doing.
Yeah. Bugs in software, right? You can see them, they trigger. Unfortunately, when you have a bug in your car, you end up getting it towed to the dealership for them to fix. And in this instance, Charlie and I sent a signal to the accelerator saying, put more gas and oxygen in the internal combustion engine. We did that for a bit too long, and the inverter in the car that makes electricity from physical motion blew up, and we had to have it towed, and I had to drive a rental car back home.
And then the dealer had to see our car, and it looked like that last picture where the dash is gone, all the computers are hanging out, and it was just like...
He's like, who the fuck are you guys? It's like, it's a long story.
Just make it drive. Don't fix any of that other stuff.
Yeah. They said Toyota states that they should reassemble the automobile entirely before they start fixing it. So don't do that. don't reassemble the car. Crashes obviously happen when you're trying to write an exploit or investigate a software vulnerability. But I think Charlie can tell you a bit more about the types of crashes that we had.
Yeah. So one time, there's something we'll show you later. I figured out a way to make the Ford's braking not work. So you press the brakes, but it doesn't actually stop you. So I was outside in my neighborhood testing that, and I got very comfortable testing that. So comfortable that when I pulled into my driveway, I didn't think to turn it off. So I was driving down my driveway, and I tried to stop, and the car wouldn't stop. So I was driving right into my garage, and I could either drive to the left and run into my house, or drive to the right and hit my actual car. And so I just kept going straight, and I just ran into the back of my garage. And you can see this is my work area in my garage, and so everything like fell off, and luckily it stopped when it hit the wall. But you can see like some more scenes from the accident. So like my lawnmower got destroyed. The table is all wrecked up. Like this is the back of my garage. It is all bowed out from hitting it. This is like the wood splinters and the sun coming in through the bottom of your garage, which is never a good sign. And then this is, again, the lawnmower that wished I had never started this project.
I think it should be publicly documented that this lawnmower is the first casualty of automotive hacking in the world. So rest in peace, lawnmower.
Yeah. And it was not part of our funding to replace my lawnmower either. Right, so unlike the academic guys, we actually released all the details, including what vehicles we used. So, like Chris said, we wanted to find the cheapest cars that had parking assist, basically. So when we would buy them, they would say like, "What color do you want?" And we would say, "We don't care." Like, "What kind of engine?" "We don't care." "What kind of color interior?" "We don't care." It's like, "Does it auto park?" And like when Chris got the car from the it showed up at his house, and I was like, "Do not sign for it until you watch it auto park itself, because that's all we care about."
The people we were buying the cars off of were very confused because we didn't care what condition they were in. I just said, "Auto park it" in front of me, and they would auto park it. It's like, "Yes, we're buying it."
Yeah, so we didn't care how many miles it had. Like anything that most people care about, we didn't care about. So this is the 2010 Ford Escape that we used. It didn't have much on it compared to Toyota. Basically, it could auto park, and then it had like cruise control and stuff, but not much. So this is a video of the car auto parking itself. So this is not hacking, this is a feature. This is what is supposed to happen. So let's see if I can get the video to play here. Just try pressing it. There we go. So this is me driving in my neighborhood. So you look, I put it in reverse, and I'm not going to touch the steering wheel anymore. I put it in gear, and I'm driving, I'm accelerating with the gas pedal, but the steering wheel turns automatically. And then the car, that's it. So the auto parking in the Ford controls the steering, but not the gears and not the gas or anything.
The car that I had was a 2010 Toyota Prius. This Toyota Prius had almost every technological package you could get on a Prius in 2010. So it had radar cruise control, which means the car would slow down if it was coming up on another vehicle. It had a thing called lane keep assist, where it knew if you were going off the road, it would correct the wheel for you. Pre-collision system, so if it really thought you were going to collide with something, it would apply the brakes for you, even if your foot was on the acceleration pedal. Yeah, and it had auto park as well, like Charlie's car. I don't think we did a demo of that, but it worked in the same fashion, that you controlled the gas and the brake, and the wheel would turn itself. So this Prius was pretty promising because it had so many technology features that we figured we could definitely abuse them to do whatever we wanted.
Yeah, and you'll see when we start getting to the attacks that we could do a lot more against the Prius because it was so much more automated than the Ford. We were limited in what we could do there.
The first thing I think we need to talk about are things called ECUs, or electronic control units. These little computers really tend to control every aspect of the automobile, from the odometer readings to acceleration to braking to sometimes steering. Auto manufacturers have realized that building these individual computers and putting in the car and writing software to do what they want is a lot more cost effective than having all the wires and all the linkage and everything hooked up, right? So they basically take input from sensors and then use things called actuators to perform physical actions, right? You could hear in Charlie's video when he was auto parking, you heard a beeping noise. That was a sensor saying he was getting close to the car behind him. And those are what these ECUs kind of do. And they're placed various places throughout the automobile. Usually the first thing people ask is, what operating system are these things running? And they're really not running a traditional operating system. It's not just some Linux variant. They're running custom code on a specific chip that really doesn't have much functionality other than performing its job. For example, there was a ECU in the Prius that was solely responsible for tightening the seatbelts in the case that you were to be in a collision. So imagine there's not much code on this device, right? Because all it does is get a signal, tighten the seatbelt. That's really all these things do. While the engine control is very sophisticated, there are ones for simple things. The ECUs, at least in our two vehicles, were generally set up on a CAN bus. And the CAN is controller area network, which we'll talk about here in a little bit. But to generalize it, all these ECUs were on the network. They could all communicate with each other and all hear each other. So as long as you were on this network, you could listen to messages that were coming from other ECUs and send messages out to the ECUs as well. And there's no real addressing, so forging messages was quite simple.
Yeah, so if you want to see what one of these ECUs looks like, this is the powertrain control module for the Ford, basically the one that controls the engine. And so this is what it looks like under the hood. It's just like a ton of wires that go into it. If you rip it out, it looks like this. So you can see there's like a chip and like a bunch of memory and a bunch of other stuff. But yeah, it's just an embedded device basically that has a bunch of inputs, one of which is the CAN network.
So we were only interested in CAN. We're aware that there are other types of networks in automobiles, such as FlexRay and LIN and other things. So I think Ethernet is even becoming popular. But we wanted to look at CAN because we figured it was our best chance to see how the car's networks work. And CAN is generally in every car, at least in America. The IDs can be 11 or 29 bits in length. We only saw 11-bit IDs on our car, and that seems to be the most common way. So instead of having an address, the ID is used kind of as a priority function, which the lower IDs are the greater priority. So the message with the highest priority in the car would be ID 0, and they contain varying amounts of data. So really, there's no addressing. It kind of just spits this message out on the network, and the ECUs on the network look at the ID, and if it's an ID that they want as input, they take the message and digest the data that's available with it. So it's really quite simple. These are kind of example messages, the first being from the Ford Escape. And this data format was invented by Charlie and I just to be human readable and digestible by our API. This isn't some standard definition. As you can see here, there's one message that has an ID, combined ID of 03B1 and a length of 8, and then followed are 8 bytes of data. While the Prius, there's another message. This one is 00B6. I remember this one. It's for the speed of the automobile. It has a length of 4, and then it has 4 bytes of data. In the Toyota, it was very common for the last data byte to be a checksum. So that 95 is a checksum of the IDH plus IDL plus length plus the first 3 bytes of data. So these messages are constantly being put out onto the network. They don't occur when something happens. The data bytes will change when certain events happen, but generally speaking, you'll see the message being spit out at a constant rate.
And then the 8 bytes is the most that a message can have.
Yeah, the 8 byte is the biggest. There's also diagnostic messages as well. These aren't constantly emitted from the car. They kind of have a addressing scheme where you send it a message and the ECU will reply with an ID that is 8 more than the ID that you sent out. So in this example, you have an ID of 0760. The ECU sees that that's a diagnostic message, so it replies with the ID 0768. This is just for a way for testing tools to be able to communicate with a single ECU at any given time. There are ways to get more than 8 bytes in a request or a response, and we'll talk about that here in a little bit. But it should be noted that these diagnostic messages are usually used by mechanics to troubleshoot problems with either physical attributes of the car or, say, the ECU itself.
All right, so 2 types of CAN messages, the kind that are always there, that we call the normal ones, and then the diagnostic ones are the ones that mechanics use, and they're mechanics tools. Sending 8 bytes of data isn't really going to cut it. So you need to be able to have ways to send more than 8 bytes, even though your sort of underlying protocol is 8 bytes. So a standard way to do it, and the way that both of ours cars did it, is using something called ISO-TP. So it's this ISO standard 157652. And basically, it's just a way to send more than 8 bytes at a time. And they do it by changing the value of the first byte of the message. So there's 0 if it's the very first one, 1 if it's, 0, excuse me, if it's only going to be one message, 1 less than 8 bytes. 1 if it's the first message, 2 if it's some follow-on, and 3 if it's like an acknowledgement or something. So I'll show you examples. That'll make sense. So here's some real CAN traffic using this ISO-TP standard. And so in the first one, it's the very first nibble is 0. So 0 says it's all going to be contained here. And then the 3 says that there's going to be 3 bytes of data. So the 3 bytes are 14FF00. And then if you want to see when you're sending lots of data, so that one only sent 3 bytes. What if you want to send a lot? So this other example, there's the 1 and the, so this one. So there's the 1 that shows that this is going to be the first of many messages to expect. And then the length is 082. So expect 82 hex bytes altogether. And then the data starts. When they run out of the first packet, the receiver sends back a 3 packet there to indicate that it received the message, and it could have some information for it, like about how fast to send it or something. But here it doesn't. And then you start to get the rest of it. So you get all the rest of them are going to start with 2. And then the second digit is going to indicate which one it is to make sure they're in order. So it's like 21, 22, 23, and so forth. And that's the way that you send data on the car if you want to do more than 8 bytes.
And those, see how it goes 21, 22, 23. What happens when you get to 2F? It just wraps around to the beginning again, and we'll start at 20 or 21. So that's, you can send, basically an infinite amount of data if you wanted.
Well, you can send F.
Yeah.
But yeah, that's like it. So so that just says how to send a lot of data, but it doesn't specify like what data to send. And so there's, you can do anything, but there's a standard, this ISO 14229 and 14230, that specify the format of the data, and both of our cars sort of followed it at times. So they specify different services that you can talk to. This is especially for diagnostic packets. So let's see. So the first thing you have to do is establish a connection with ECU. If you're, say, a mechanics tool, you have to, say, get ready, I'm going to do something with you. And so the way we do it here is it's ISO-TP, expect 2 bytes, 1003. And so 10 by the specification says this is a diagnostic session control. And then the 3 says something else. It's like a parameter. And then the ECU responds back. You'll notice it's 40 more than the 10, and it's always like that. So it always responds back with 40 more if it's succeeded. And then what do you get? 3, which is correspond. It's like saying I'm acknowledging that you sent a 3. I'm acknowledging that. And then finally some information about it. You want to do security access?
Yeah. Security access is an interesting one because this functionality is usually needed when you want to perform privileged operations on an ECU, such as reflashing the firmware or performing certain diagnostic tests that could be considered dangerous. So what you see happens here is you try to authenticate, and we're sending 2 bytes, and then you see 2701. That's just saying, hey, I need the seed that I'm going to use to create this response to let you know that I'm authorized to do stuff to you. The server then sends back the 67, which is 40 more than 27. And then in this instance, there's 3 bytes, the 54, 61, B6. That is going to be used to compute the key that will be used to unlock the ECU for privileged functions. An algorithm happens on the programmer, which is, our point is our laptop, and it sends it back. And by sending back the key derived from the seed, if it's wrong, you won't be able to get privilege access. If it's right, it sends back 6702 saying, yep, we're good, you requested that privilege level, and we're going to be able to do privileged stuff. And we'll show you kind of here later how we derived how to create these keys for each of our cars.
All right, so basically you're proving to the ECU that you should have privileged communications by using a proprietary algorithm and their key to compute a response. So it's kind of like a password. They don't publish what the algorithm is to use, but we'll talk later about how we figured that out. Sure. Another type of message you can send, diagnostic message, is input-output control. And so basically the idea is in testing, maybe you want to test what happens when some sort of sensor reads a certain value. And so this is set up to tell the ECU, pretend that your sensor has this value, or pretend the person is pressing the gas, or whatever, and then you can diagnose problems as a mechanic. So again, here you send 2F is the one that says it's input-output control, and then you send 2 bytes to indicate which input-output control, so like which sensor, and then some parameters. And this seems really promising at first. You're like, oh, I can just send it and tell it to like crash itself or whatever. But first of all, it will ignore you most of the time. And second of all, there's no document to indicate what 0307 is. You have no idea what that's going to do. And so you would have to try every value. And if you'd had the wrong parameters, then those wouldn't. And so it's actually very difficult because you have no idea how it works and how to get it to work. So there's lots of other ones besides the ones we've talked about. Read memory by address, request download, transfer data, write memory by address. When you read the document, you think this is going to be very easy. I can just read the memory, I can figure out what to do, and I can write the memory. I'll be done. But at least our cars, the ECUs basically do not implement almost any of these. So it's very difficult to get the firmware off, and it's even harder to write firmware to it.
We got really excited when reading the ISO spec because, like you said, we'll just rip the firmware off, reverse engineer it, that's what we do, and then write it back on there. Needless to say, the Toyota supported none of these, and I think Charlie's only supported 2 of these services. So, if you're doing this work and these services aren't supported, don't be surprised. All right, so now we're going to talk about the tools that we use, mainly the physical tools that we use to perform the functions. The first thing we used is a thing called an ECOM cable. You can buy the regular cable, I think, for like $150 US. You can also buy a special Mechanics Edition for $1,200. We would recommend not buying the Mechanics Edition because if you look at the wiring diagram, you can snip a few wires and buy an ODB2 shell and put the wires in the appropriate place, and it serves the same function. Basically, the expensive one just has exposed wires.
Now, the expensive one also comes with software, which isn't as good as what we released. So.
Yeah. So save yourself some money if you're going to buy one of these. Just buy a regular ECOM cable, look at the wiring diagram, and our paper explains to you how to snip the wires and connect them to an ODB2 shell. One of the items that I used a lot is a J2534 pass-through device. This is a car DAC Plus. This is a couple $100 US, and this was a way for the software that we downloaded from Toyota that the mechanics use to communicate with the car. So basically, most mechanic shops will have something very similar to this. It's just a standard way for software to talk to the automobile through the ODB2 port. If you're going to do this research, buy a lot of these. They're like 20 cents US. Basically, it's a shell that is blank for ODB2, and you can put metal pins where the pins are in your car. The standard pins are 6 and 14, but Charlie had pins for the Ford that were different, so he could create his own kind of device instead of hacking up a whole big cable. Well, since we showed you the hardware tools, now we'll explain the software that we wrote, which is now publicly available online. You can download it and use it yourself. The first thing that we really wrote was a thing called ECUs. And as you can probably guess, this was software that leverages the ECUs cable to read and write onto the CAN bus. It basically was our Swiss Army knife, right? We would sit there and read messages on the wire, and we built in some functionality to send multiple messages, continuously loop messages, filter on certain IDs. It's not very well written, I would say, but it definitely serves the purpose and is very useful. This is a tool when we wanted to figure out how parallel parking worked. Charlie and I would be out parallel parking our cars for hours on end for a couple weeks, looking at our computer and using this software to narrow down the IDs that were used for the parking. The other portion that we wrote is the ECUs API, and it's basically a Python API that is quite useful and leverages a lot of the functionality of the ECUs program, which is written in C. This just makes it really easy to write a 5-line script that performs some action. And you'll see in our examples, we're actually using our own API to write the little programs in Python to control pieces of the car. And then we also wrote this other portion called PyEcom, and it really just abstracts a lot of the ECUs API library, especially for the Toyota, since the Toyota was quite different than the Ford. There was a lot of different functions that were needed, so we figured creating another wrapper library would make it easier to do stuff. So I'm a color by numbers type of guy, so an example makes it easy. If you're using our ECUs API, the first thing you're going to do is plug the ECUs cable in your computer and hook that up to the car, and then you open the device. After opening the device, you can set up we call it debug line to SFF. It's basically the format that we invented. It's text, and then you can write a message onto the CAN bus for a certain amount of time. So you can see in literally 4 lines of code, you can continuously write messages to the CAN bus. This was one of our goals. We wanted to bring this research to more people, so you didn't have to spend the time figuring all this stuff out. You can download our library, start sending messages to your car or reading messages quite easily. We have other functions such as writing messages, write a message from a file, so you can actually take a dump like you would in Wireshark to a file and then input that file to try to recreate a scenario in the car.
All right, so now let's talk about, now that we can write messages, what types of messages can we write and what can we do to the car? So it should be said that at first we kind of wanted to do everything. We want to control steering, brakes, acceleration. But there's some things in the car that you just can't control with CAN messages. And for example, in the Ford, there's just no way to control the throttle, the gas. Because all that is in one ECU. So there's no communication on the CAN bus to tell the ECU how to behave. It has all the state that it needs inside itself to make all the decisions. So there's no way you can control some stuff.
It's taking a physical state of the car, an angle that the pedal is pressed, and taking only that as input, not messages from the network.
Right. You could completely snip the CAN wire and that would still work. So there's nothing you can do there. Another thing is that we can forge messages and that say to do something like maybe turn the steering wheel, but the original messages are still going to be there. So there is an ECU still sending the real state of the car, and you can put other messages on top of that, but there's always going to be a fight between the real messages and your injected messages. And then finally, the car makers build in security, or I should say safety, if there's a different word for Chinese, that to try to prevent accidental things. So if a message is corrupted, they don't want the car to crash. So there are a lot of precautions that they put into it that either stopped us from doing something or at least made it more difficult to do things. All right, so again, there were two types of CAN messages, normal and diagnostic. Let's first talk about what we could do with normal messages. So, what's that? Yeah. So the first thing is, it's pretty simple, but people seem to think it's cool. You can control the speedometer on either car. So we'll start with the Ford one. So here, the ID you need to know is it's 0201. And the only way we figured that out, like that's not documented, was just trial and error. So it has 8 bytes. The format looks like this. You take your speed, you put it into that formula. You take the RPMs, plug that into the formula, and then you get the steering wheel you get the speedometer to say what you want. And so if you want to see how easy it is, if you use our API, it's essentially 2 lines of Python to set the speedometer. So here's a video. So I'm driving down the street. I'm driving quite slowly. It looks like 15 miles an hour or something. And then now it says I'm going quite fast. But I'm not actually driving quite fast.
And this is obviously a closed course around Charlie's house. We're not endangering his neighbors.
Yeah, this was very safe. So, and then here's the same thing on the Toyota. So for the Toyota, it's a different CAN ID, a different message, but it's the same idea. It's one message you play continuously.
As you see, I'm sitting by my garage. I'm not moving at all. Yep, I'm definitely not moving. And then you can tell the car that it's going quite fast, 20 miles an hour, and you're not moving. So you can forge both these messages for the automobiles to trick the speedometer into thinking it's going any speed you want it to. And you'll see later why that's actually important for other types of things we wanted to do. For the Toyota, we wanted to be able to arbitrarily apply the brakes. And the way we did this, again, I would drive the car in cruise control really close to another car and have my sniffer hooked up, and I would see the car brake. I would record the traffic. We would sift through the messages and figure out which ones are used for automatic braking. Again, you kind of plug in how much force you want to apply to the brakes. Obviously we wanted to clamp them completely shut. And then there's a checksum, and then there's an adjustment state, which if you read the paper, it explains what that is. Again, while this is a bunch, this is the whole program to completely lock the brakes of a 2010 Toyota Prius if it has the pre-collision system. The brakes will be applied at full force regardless of how fast you're going. You can even press the acceleration pedal the whole way down and the car won't move. So we have a video of that. Okay. Where's the sound? Well, there's usually sound.
Right, that's what it sounds like.
So, yeah, that's what you generally would have heard.
Let's watch it again.
Okay. Did we get sound a second?
Yeah, there we go. So you can see we're driving like 40 miles an hour. I don't know what that is. Like. And then we send the packet and we stop.
That was pretty abrupt.
All right. Go ahead.
For the Toyota, we could also control the steering. It had the lane keep assist, which was one way of controlling the steering, but it also had the intelligent park assist, parallel parking the car. Again, we just parallel park the car with our sniffer hooked up, for hours on end trying to figure out what messages and what data corresponded to, say, the angle of the wheel, things like that. The Toyota actually had a lot of restrictions on when the wheel could turn if you were using the park assist. You needed to be in the park assist mode, the car needed to be in reverse, and the car could not exceed more than 5 miles an hour. So at first it seemed pretty daunting, but what we did is figure out a way to trick the car. So before you saw how we set the speedometer to 20 miles an hour, this time around we gave the automotive network a speed that the car couldn't go, so no one knew what to do. From there, we told the car that it was actually in reverse when it wasn't, and that it was parallel parking itself. So by combining all the knowledge we learned about the car, we could make the wheel turn. Again, as Charlie talked before, it's not really smooth like it would be if you were parking the car, but it really jerks the wheel out of your hands and you can definitely wreck. We just wrecked someone giving a demo last week.
So yeah, there were 2 ways in the Toyota that you could turn. You could do the lane keep assist, and the safety built in there was you could only turn 5 degrees. So that's not very fun.
No.
And then the safety for the parallel parking was it only worked if you were slow and in reverse, and that wasn't fun. But so by tricking that, we were able to get the turn. So here's us driving again, and me actually.
I think it should just
So Chris is going to make the steering wheel turn to the left. So it did a little bit there, but there it did quite a bit.
I was literally trying to kill Charlie the entire time.
It's quite scary. So here's like if you're driving what it would look like. We almost hit a little tree on the side of the road. It always seems to turn when it senses you're going to crash.
Yeah, it's
Like,
really weird.
Yeah.
But as you see, we didn't really have full control, unfortunately, but it's definitely enough to wreck you. Acceleration was another one of our goals, and the Prius actually had acceleration by wire. That is, it communicated on the CAN bus to a certain ECU, and that ECU kind of controlled the speed of the car. While in Charlie's car, it really didn't work that way. Again, we figured out the CAN ID that was used for acceleration. Unfortunately, for this example, we couldn't be in the ODB2 port. We actually had to connect into another place in the CAN network, but we figured if you're going to compromise a car, you're probably going to get multiple entry points after you've gained your initial entry point. So it's still feasible, and it showed that we could control acceleration of the automobile. Again, this is the whole program. As long as you're jacked into the CAN network in the right spot, these couple of lines will accelerate the automobile. The Prius is a hybrid synergy drive, so the gasoline engine isn't always doing all the work. You know, the electric motor will help the car out. So this really only works when the gasoline, the internal combustion engine, is engaged and will end up, making the car go forward. You let off the gas pedal and you send these messages and the car continues to accelerate. Warning, this can and will harm your car. If this was my personal car, I wouldn't have done any of this work, but specifically, I would have not done this because we did blow up an inverter. It cost us $4,000 USD to fix and took a lot of budget out of our project. So here's a video of us accelerating. It's really hard to show, but you'll see that I lift my legs up to prove that I'm not pressing the pedal, and hopefully you'll hear the car continue to accelerate.
If you look close, you can see the speedometer go up too, but it's tough to see.
If we would have let the camera roll 2 more seconds, you would have heard this loud pop, and that was the inverter blowing up, and the car never worked after that.
Yep, so yeah, don't do that. So that was just sending normal traffic that the car normally would send, except we've sent things that it wouldn't normally send. Now we're going to talk about using the diagnostic messages to affect the car. So the first thing you have to do if you want to send diagnostic messages is you have to know how to get around the security access. And so the way that the security access works is you need to know the algorithm and you need to know the secret for each ECU has a different secret value that only it knows. But it turns out there's not only do the ECUs know, the mechanics tool has to also know. So the way we got it was we basically just reverse engineered the mechanics tools. So this is an example. First of all, so there's an ECU in the Ford called the Parking Assist Module, PAM, and they actually screwed this one up. So the seed that it sends is supposed to be random, and every time it's supposed to be different. Here, it always sends 112233, which is wrong. So as long as you see this once, you know that the answer is always going to be the same, and you can send it without knowing the algorithm or the secret. So they screwed up that, but all the rest of the ECUs, they did the right way. So the way we had to do that was we had to reverse engineer things.
Yeah. Which shockingly was probably one of the easiest parts for us to do. We had Windows 32-bit software, and we had to reverse it to get the keys out. That was literally probably the easiest thing we did in this entire project, at least for us.
Right, because we know about software, we don't know so much about hardware. So this is what the Ford tool looks like. It's like straight out of 1990. And you can reverse it, and they actually had some anti-debugging built into it, but it was very trivial to get around. So this is the actual algorithm they use to compute the security response, and this is in hex arrays. And then here's all the keys dumped out of hex arrays. So you can just dump them out and see what they all are for every ECU, for every Ford. And then because they're 5 bytes, they can be any random bytes, but sometimes they made the bytes ASCII characters just for fun, I guess. And so I got a real kick out of seeing what some of them were. So here's the actual keys that you need to know. So there's a list of like 60 keys or 100 or whatever. But these are the ones that are actually in the 2010 Ford Escape. So, and then sometimes you have to authenticate to get even higher privilege. It's like authenticating and then getting root or something, and those are those keys. So we have all the keys, and we can pretend we're the tool.
The same went for the Prius. There are a few more keys for Toyotas, Lexus, and Scions, but generally speaking, for the updatable ECUs in my car, it was a simple XOR operation with one of these 2 keys. We reversed that right out and boiled it down to make it easy. So if you check out our tools and the paper, we show you if you want to do security access for Toyota, Lexus, or Scion. There you go.
So here's one. And it turns out that there's lots of ways to denial service the car with the CAN bus. You can make the car not work or not do anything. So that's actually like very easy to do. So here's one example you can use to do it. In this case, you just send this message and the car will die. The engine will die and you won't be able to start it as long as you send this message. So here's that video. So I'm driving, you can hear the gas, and then you hear it stop. And then I'm trying to start the car, and I'm rolling backwards.
Did you kill the engine?
That's my cameraman, son.
Yeah.
So anyway, so you, no matter what you do, you're out of luck at this point.
Yeah. We can do things like turn the lights on and off for the Toyota. They usually have to be in the auto state, which I think a lot of people keep it on. So when it gets dark, the lights automatically turn on. You know, you have your daytime running lights. We wanted to do a demo, but unfortunately, I planned to do this demo after we blew up the car. So I never got to do a demo of this, but you can turn the lights on and off in the Prius.
All right, so same thing in the Ford. You can turn the lights off, and this one is kind of especially scary because not only do you turn off like the headlights, you can turn off the brake lights. So even when you press the brake, the lights don't turn on. It's just like completely dark. Here's a video, I think. I'm about to DOS this time. So anyway, so I send the packets, and then the interior lights are on there and the speedometer, but the outside lights are off, and like the air conditioner doesn't work, the radio doesn't work. you'll see like I open the door, but the dome lights don't come on. I'm pressing the button, and so none of the lights are on, including the brakes. So it's sort of a bummer.
Can't get out of park.
Oh, and I can't get it out of park either, which is sort of funny because it's disabled the thing that makes sure that you've pressed the button to get it out of park, and so I'm like totally stuck.
One of the funny ones I thought in the Prius was that you could send diagnostic messages to engage the horn of the automobile, and as long as you sent this message, the horn would honk forever, which we annoyed Andy Greenberg from Forbes with.
Oh my God. What happens if I can't do anything?
Again, it's not really malicious, but it is annoying.
And it keeps playing even if you turn the car off.
Yeah, even if you turn the car off and you're playing the message, the horn will honk for just about ever. My neighbors are probably upset with me for testing that for several days. The seat belts, as I mentioned before in the Prius, were linked up to the pre-collision system. So if you were to be in an accident, they would pre-tense the seat belt to ensure that you didn't smash your face into the windshield. We found that we could just continuously send these diagnostic messages as well and tighten the seat belt. Annoying. I don't think it could really hurt you, but it is weird.
Fight it! Fight it!
And again, we really annoyed Andy Greenberg with that. When he was driving a car, we'd randomly just tighten his seatbelt. Locking and unlocking the doors, again, was used through diagnostics. It was pretty trivial. I think these would be good candidates if you had a remote vector. You could at least gain physical entry to the car. Again, I plan to make these demos. The car blew up. I never got to make the demo. Fuel gauge. Even the fuel gauge is reliant on things such as the CAN bus. Even though it measures how much fuel is in there, you can test the gauges with diagnostic tools, right? So if you watch the video,
I can pretend that we have a full tank, and that even works.
You can say that you have a full tank of gas.
While you're driving.
I'm looking for a friend with a Prius because I want to get one of these little plugs that constantly plays the message that he has a full tank of gas, so he just breaks down, and I can laugh at him.
So here is like the thing that made me crash my car into the garage. It's probably one of the scarier things. It's a command that a mechanic would use to bleed the brakes, like let the air out or whatever. So they did build precaution, like security into it. It only works if you're driving like around 5 miles an hour or less. So that means that if you're driving like 40, the brakes still work. But the problem with that feature is that if you want to use your brakes, at some point you want to actually stop. So you always want to eventually go less than 5 miles an hour. And so you can't stop. So here is a video of me doing it to Chris for a change. So he's going to go park the car, and then I'm going to make the brakes not work when he goes to work.
I found a spot. All right.
So that noise is the brakes bleeding. So we're driving like into the weeds and stuff.
I was panicked enough to try to use my left foot to press the brake pedal. I don't know why.
If you see, like, we hit the curb and, like, go up, and then we're driving, like, into the weeds and stuff. And the only reason that he ever stopped, when he was mashing the brakes with his foot, he actually knocked the cable out. So otherwise I would have made him drive until he hit something. Yeah, one of the scarier parts of that is the annoying noise that it makes. It's like you're driving also, it's like, it's like anytime I hear that noise, I'm like, oh shit, the brakes are not working. But yeah, so I think we're gonna probably have to skip this. So if you want to learn more about the firmware, get our paper. We'll just skim over this really quickly because we're running out of time. But basically, the way that we did it for the Ford, the Toyota we're still working on, was to watch the way that the mechanics tools updated the firmware and then try to figure it out from there. So we could do it for 3 ECUs in the Ford. So I had to actually physically the board out and use a hardware debugger to dump the firmware. So that's quite difficult compared to using just stuff on the CAN bus. So I used this guy, this HC12 development kit. And then once I had firmware, there was actually already a module in IDAPRO to disassemble it, so that made it easy. So I disassembled the whole thing, and I could figure out like how it worked, and it's pretty easy in the embedded world to reverse things because there's particular things in hardware that tell you exactly what's going on. So you know at some particular address, that's where the CAN stuff happens. And so it's pretty easy to reverse out like where all the interesting CAN things are. And you can find like the big switch statement that handles it and so forth. So check out the paper if you want to see more information about that. So here's a video just to show that I can do that. So what I'm going to do in this video is I'm going to plug into the CAN bus. I'm going to reflash the firmware on one of the modules and make it do something. In this case, I'm going to make it send out a packet over and over that tells the car that it's in reverse. And one of the things that means is the backup camera comes on. So the backup camera will be on even though I'm not in reverse. And then what I'm going to do is I'm going to unplug from the network to show that I don't have to be on the network anymore. I just need to plug into your car for 5 seconds and unplug, and I can still control the things in your car.
Yeah, if you're familiar with malware, right, this is persistence.
So I plug into your OBD2 port for a second. I run my program. So there's the program. That's all I can pull out an OBD2 part. And yet when you're driving along, so I'm driving up. You've got your backwards camera still on, but my car thinks I'm in reverse. The ECU, and again, this truck in front of me, I knew he was there. Even though I'm no longer connected to the OBD2 port. Pretty cool, huh? All right, so anyway, that just shows you can flash things and change the firmware, and it'll survive even if you're not on the network anymore.
Yeah, he could have done any other of the operations he didn't afford, such as, you know, bleed the brakes and things like that. Obviously, the backup camera was the safest option. The Toyota is really weird and really proprietary. Unfortunately, we don't have much time. It didn't actually use the request upload and request download things. They do their own proprietary thing. Shocking, you know, that the Japanese auto manufacturer would do that, right? But they have these calibration files that contain stuff in them. A lot of it's in Motorola S format, so you can actually get the, you know, calibration updates for the car from Toyota's site and then pull them out of here. But you can only really, you need a special password before you can actually do reflashing, and it communicates on these really low CAN IDs. Unlike Charlie's car, he could do security access and then reflash. I had to do security access, send this kind of one-time password for the given calibration, and then figure out this proprietary communication protocol between the computer and the ECU. So we're still kind of working on that, but if you're interested, read the paper. There's like 10 pages of information that will tell you how we went about doing this. So the final thing I guess we're going to talk about is how you could, now that we know this, how you could actually detect these attacks in your own car. And so it's pretty easy to spot ours. The packets you see are very regular, very expected, nothing unusual. But when we send our attack, it looks very different. It's a flood of packets. So the way that we get the car to ignore the real packets and listen to ours is we just flood the network, and then the car listens to our packets. And so this is a histogram of the types, the rate that you see messages, and our attack would be like way off the chart. So if you just kept track of the rates of messages, you would be able to detect the kinds of attacks that we did in this research. Yeah, I mean, for example, the steering one, we needed to trick the car into thinking it was going a speed that was, you know, below 5 miles an hour. It received a speed packet maybe 10 times a second. We sent it 10,000 times a second. So we just literally flooded the network. Yeah, so there are things that you can do to detect these. A lot of the diagnostic stuff, like Charlie bleeding the brakes, should never occur when the car is driving. But, you know, those are safety mechanisms that the manufacturer can fix and maybe should do something about. Do you want to talk about this?
Sure. So we sent this to Ford and Toyota before we gave the talk about this at DEF CON. And so Toyota basically said that this is no big deal, that they focus on stopping remote attacks, which I'm sure is bullshit, but what we can't prove otherwise at this point. But they basically said that what we did isn't even hacking. It's like, you know, what's supposed to happen there. which I know.
Which is definitely untrue, right? That's like saying, don't worry, I have a firewall. All my computers behind it are safe. It's fake.
Yeah, so they more or less say that if you can get a remote attack, you can crash the person, and they're okay with that. So to wrap things up, there's this thing called a CAN bus, and all the computers listen to it, and you can send messages. If you can send messages on the CAN bus, you can trick the computers into doing things they probably didn't want to do. And then, a big part of our research was releasing all the information, all the tools, so you can check it out on the internet, download the paper. It's like 100 pages or something, and download all the tools and try it out yourself.
Yeah, we have all the tools, even the data from each one of our cars, so you literally could recreate exactly what we did.
Right, we have IDAPRO dumps of the firmware and stuff like that. So thanks to these guys who helped us out, and we can take a couple questions if you have any. All right, thanks.
Yeah, thanks everyone.